events, definitely feel free to let me know. Beyond the Seattle chapter, we also have a lot of sister chapters all over the world. So we are a very big family. So about the Women in Machine Learning and Data Science Group, we are a nonprofit organization. Our mission is to support and promote women and gender minorities who are practicing, studying, or simply interested in the fields of machine learning and data science. So we aim to create opportunities for members to engage in technical and professional conversations by hosting a variety of events, including Tech Talks, which is the one we are going to have tonight. We also have other events like workshops, networking events, and hackathons. Yeah, I will post this in the chat, so definitely follow up our Meetup page for future events. We also have a Twitter account, and if you have any questions, feel free to email us here. Yeah, so we also have a YouTube channel, and tonight's event will be recorded. And actually, let me show I hit on the record button. Will be recorded and posted on the YouTube later on.
I already started recording, so you're all set.
Okay, awesome. Thank you so much. I think, yeah. Okay, that's good. Okay, so next one. Yeah, so for tonight's event, we are going to have 3 tech talks from 3 amazing ladies, and Anna is going to be the first one. Skylar is the last one. So the first 2 talks are going to be live events. And the third talk is going to from Katinka. She's in Italy now, so she has recorded her video, and I will just play it, share my screen with you guys, and I will also share the YouTube link. So if the Zoom over YouTube quality is not great, you can always just watch it in your own computer. So every talk is about 20 minutes, and we are going to have 10 minutes in the end of each talk, so we can do Q&A. For this online event, so I will encourage everybody, since you guys are muted, like post your questions in the chat. And in the end of each talk, I will go through the questions and let the speakers answers to them. So for the third talk, the recorded talk, also feel free to post the questions in the chat, and we'll gather the questions and let Katinka respond to them in our event meetup page. Okay, so yeah, the original plan is for this event to go live on YouTube, and but I have some trouble on doing with it, but I can try to do it again once the speakers start to talk. Okay. Okay, all right, yeah. Without further ado, let's kick off tonight's Tech Talks. So the first one will be Anna. I'm delighted to have Anna here. Anna completed a PhD in physics from UC Irvine in 2017, where she researched astroparticle physics. Afterwards, she moved to Seattle to work in data science. She is currently working at Vulkan on a team dedicated to improving climate models. So please join me in welcome Anna for talking about improving climate models with machine learning. Awesome. Anna, I will stop share screen and let you share the screen.
Thanks, Sophie. Also, yeah. I should mention, I should have written in there, I also worked at Zillow before I was at Vulkan. So
yeah,
part of the big Zillow crowd here.
I know, yeah.
Okay, is this full screen? I think it should be.
Yeah, it is.
Okay, great. Yeah, so hi everyone. I'm going to be talking about how our team at Vulkan is working on improving climate models with machine learning.
Nice.
So just a little bit of background about our team. So we're an open source philanthropic project of Vulkan Inc. here in Seattle. We sort of have 2 different working areas within climate science. So the first half of our team is people working to make climate models run, or sorry, not climate models, but working to make high resolution models run faster using a domain specific language and modern computing architectures. And then the second team that I'm on is trying to use machine learning to improve the accuracy of rainfall predictions in global climate models. Okay, so to give some background and motivation for our research, I'm showing a couple of figures here that are an ensemble of different climate models predictions for temperature and precipitation in the Pacific Northwest region over the next 55 years. So you can see that in this left figure here, while climate models are generally in very good agreement in predicting increasing temperatures in the coming decades and agree on regional scales generally, they have a much wider disagreement here on the right, you can see, in their predictions of rainfall in a warming climate. So that's why the main goal of our team is to try and reduce this uncertainty in climate model predictions of future rainfall trends and extremes, because obviously these have a huge effect on society and people's lives. So a very obvious question to ask then is, why is there so much uncertainty in rainfall predictions as opposed to temperature? And the reason for this is, so I'm showing a little cartoon here of sort of how a climate model divides up the Earth. So we simulate climate into the future by dividing the atmosphere into a grid in both the horizontal and vertical directions. And then we evolve the atmospheric quantities like temperature and humidity within each grid box, time step by time step, using the equations of fluid dynamics and physics. This is really computationally intensive. And because you have to run a climate model for decades, because that's sort of the timescale that we're interested in order for a 50+ year-long simulation to run to completion in a reasonable amount of time and computational resources, we need to limit the resolution of these grids that we're running at. So a typical scale for a climate model might be a grid box that's like 100 by 100 kilometers on each side in the horizontal direction. However, as you can sort of see in this picture here, a lot of physical processes, like if you think about like clouds and stuff, if you look at the sky, they are described at much smaller scales than 100 by 100 kilometers, right? So for example, convection is really important for precipitation because that's a physical process that leads to thunderstorms and very heavy rainfall. And that is described at a scale of a few kilometers as opposed to 100. And sorry, I should also point out in this purple box here, this is sort of the movement that's being described by convection. It's sort of a more up and down in a column of air as opposed to side by side. So obviously a climate model can't directly simulate convection because its grid box is very low resolution. So instead they use what we call a parameterization in order to approximate the effect of convection leading to rainfall. And there are a lot of different ways to construct a parameterization and a lot of like hand tuning and different approaches. So there's a lot of differences between different groups parameterizations. And because this is responsible for a lot of rainfall, a lot of uncertainty in the precipitation forecasts. Okay, so I just mentioned that the convective processes that parameterizations are used to approximate are of order a few kilometers in scale. So there are simulations that actually can run at resolutions this high. For example, the ones that the other half of our team is working on are these high resolution simulations. So I'm showing an example here of like, this is the level of detail that these produce. And so these are sometimes called global storm resolving models or cloud resolving models because they can actually explicitly simulate the convection that's going on without having to resort to these parameterizations to approximate their effects. And these high resolution simulations typically do a much better job at predicting precipitation than the low resolution of climate models. But on the flip side, because they're so detailed, they're too computationally intense to run for decades. So like the goal of the sort of domain specific language half of our team is to get one of these able to run for like a few years. Like that's considered a long time for a fine resolution model. So the strategy that our machine learning team is pursuing in order to try and improve climate models predictions for rainfall is to use machine learning to augment a low resolution climate model and try and make it behave more like a high resolution model. But it's still going to be able to run at the lower computational cost of a low resolution climate model. Okay. So now I'm just going to talk a little bit about what goes into and what comes out of our model. So to construct our training data set, we use both a low resolution climate model and a high resolution simulation. And these are sort of run over the same time range. So for our prototype, we do just like 40 days, which obviously isn't a climate time scale, but is enough to sort of, try and test out different models. So at each time step, we save the state of the atmosphere from each model. So we have like the low resolution one that we're trying to improve. And then we have the high resolution one, which is sort of our target. And then we downsample the high resolution state to match the lower resolution. So this is sort of an example of what we're doing here. We're going to take our target, which is this really detailed thing, and then downsample it to sort of a blurrier looking data set. Okay. And then each column in the atmosphere, so remember back in this picture, this is sort of like one column of air at a point on Earth's surface. So each column is going to be one training sample. And then we have some vertical profile of like air temperature and humidity and some other quantities. So the inputs to the machine learning are the state of the column. So it's like temperature, humidity, maybe like angle of the sun at that time of day. And then whether the surface is land or sea. And then the outputs that we're going to try to predict are the changes to the temperature and humidity in that air column due to the effect of convection, okay, which again, we can't resolve that directly in this low resolution data. So again, just to reiterate, our goal is to make the low resolution model behave more like the high resolution data. So one kind of interesting thing about this particular problem is that the way we evaluate our machine learning skills, so what we call offline skills, like what you kind of traditionally do in machine learning, where you have some holdout test set, and then you measure the model skill just based on that holdout test set. But with the way we're saving our data, that really only measures how well this model does on a single time step of a climate model, which is like 15 minutes, right? So that's not necessarily that useful, and it doesn't really tell us about whether it's going to do well in future predictions, like years down the road. So the more important way of evaluating this is what we call the online evaluation. So that's when we take that machine learning model and actually plug it into a running climate model, so that each time step that machine learning prediction gets fed back into the model and influences the model on the next time step. So you can imagine that it's really easy to sort of get into a feedback loop if your model's not behaving well, where it sort of pushes the atmosphere into a crazy state. And that just makes the machine learning model make even crazier and crazier predictions, and then your simulation will crash. Okay, how am I doing on time? I'm at like 17 minutes. Okay.
I know.
Don't worry about the time.
Oh, that's time? Or
I just don't worry about the time. Yeah,
oh.
we have plenty of time. Yeah.
Okay. Yeah. So for this audience, since it's like a machine learning group, I think like maybe the most interesting things to go over are sort of the two different models that we've tested in this research. So our team actually uses both random forest and neural networks. And sort of when we use random forest, they work really well out of the box. So for example, like we don't really have to tweak hyperparameters that much at all to get a working, a model that works well in the online validation for random forests. Whereas for neural networks, there's a little more hand tuning and setup involved in the beginning. But we can also, get a neural network that runs in a simulation. And the big important thing to note for these two different models is that property of random forest, where they don't really extrapolate outside of the domain of the training data that I've seen. whereas the neural network will, bravely extrapolate if you give it a new point that it hasn't seen before. So this, yeah, so this makes it for really good performance in the offline setting for neural networks. And we typically see that they do better than random forests, which I'll show in just a little bit. But it also makes them a lot more finicky when we go and plug them into a model and couple it to the fluid dynamics, because it's pretty easy for a neural network to give some pretty extreme predictions. Okay. So here's an example of an offline prediction of a random forest model versus a neural net. And then on the left here, we have sort of the target data. So you can see that the neural net is generally doing, they both get the large scale patterns, but the random forest isn't really getting any of these areas of cooling. It's basically doing mostly heating. And the neural net is doing a better job matching the amplitude to the random forest. Doesn't get the full amplitude of the training set targets. And then here's an example of a neural network that actually blows up when you go and plug it into a simulation. So basically this black line here is what we use as our baseline for comparison. So it's just the sort of the regular climate model that doesn't have any machine learning, and it's using its regular parameterization to describe convection. So you can see that runs in just a little bit, but it doesn't crash. And then this blue line here is a neural network that we trained that didn't crash. And then what I tried was, let's try and add some additional outputs. So let's try predict wind as well, and do some momentum corrections in this model. And so I don't have it shown here, but the random forest just handles this really easily. You just have it, predict some momentum, and it still runs. Whereas this green line here is a neural network that's trying to do the same thing, and it just goes crazy. We have made big improvements in keeping neural networks stable. So I don't want you to take away that this is what they're all doing. I'm just trying to show the dangers of using a neural network in these simulations. And one interesting thing that you guys might appreciate is a really easy way to increase the stability of a neural network is to just use a mean absolute error loss instead of a mean squared error loss. Since it's going to make the machine learning less sensitive to outliers in the training data, and therefore less likely to predict an extreme value when you use it in an online setting. Okay, almost done here, so I won't spend too long on this slide, but the point is just that these models do have increased weather forecast skill over our baseline, which is good. So basically what this is showing is that you get about an additional day in forecast lead time improvement if you run a model with the machine learning parameterization. Okay, thanks for listening. And I'll just leave you with this fun little animation. So this is a high resolution model, and then this is a machine learning model that was trained to try and replicate it. This is showing, I think, rainfall over a day or two.
Oh, awesome. This is really cool. I didn't know you can just make the world map to flat and just watch all the rain. How do they flow? How do the air and water moisture flow? This is very interesting. Yeah. So the application is more about global model, and the units maybe several kilometers, several hundred kilometers. It's not about within a city, you can see when it's going to rain.
Right. Yeah. So even in this high resolution video, this is actually downsampled from the original high resolution at 3 kilometers, because that would have been way too much to make a movie of.
Yeah.
Got it. That makes sense. Yeah. Awesome. Thank you.
And I'll actually talk about applications a lot. So it's a nice tee up.
Yeah.
I actually have a question, Anna, that I could ask you that's kind of relevant. So kind of, and I even teed this idea. So my talk will absolutely be about the application of models like these our team does less ML, right? And does more just ingesting kind of a lot of the downscaled models that other scientists have done. The temperature and precipitation, any of the meteorological variables that we use in ours, it's a public data source, but the resolution is 3.1 and change kilometers squared. So according to, like you, that would be like very high resolution. I don't think I saw in reading the methodologies of that work that it was driven by machine learning that they do that downscaling. It looked like kind of a little bit more, I don't know, what do you think it was, are there other techniques that are kind of not machine learning, but maybe more, I don't know, kind of your traditional kind of statistics relationships? Because I know that it's not necessarily the modeling that they've done, because I know that there's the two sources of downscaling where you can, model it out, right? Simulate it, then you run the simulation into the future, or you take kind of the global projections and then you use the statistical relationships between like global averages and local locations to then, I think that's the technique that our sources kind of use. Is there, when you think about, you said that this is publicly, you guys, this is, this will be public stuff that you guys do. And when you present these, have you compared kind of what you'll be capable of versus those public sources? Or?
Yeah, no, that's a good question. I'm unfortunately not very familiar with those sources, but you said, so it's like you're saying 3 kilometer scale projections out decades?
Yeah.
Huh.
To 2060. Let's talk offline.
Yeah, that'd be really interesting.
Because because we're building product off of it, right? And it's like a public source is like validated by, climate scientists. So you like to think like, oh, okay. Like, but let's talk offline. I want to talk about, different.
Yeah, I'm really interested. Yeah, I don't think it would be like a directly simulated thing, but yeah, I'm sure they have other,
Yeah. And then I haven't done a lot of thought yet into like, and maybe you would have already done this thinking. So let's definitely talk about it. I'll buy you virtual coffee, but like, what are the advantages, right? I mean, because in one situation, maybe in this statistical model, I can get more local, but I'm not really getting local with any kind of accuracy maybe, or I'm, I don't know how they've, how do you validate into the future?
Awesome. Like it's always exciting to see people got connected in our like events, and maybe we can start a panel about it next time.
Yeah. And Tia just asked, I'm talking about these regional downscaling where global models feed more localized models. That's what I am talking about. That's like our sources that I'll talk about next for climate check. They've done that work to do the downscaling. We have advisors that help us do that with drought and wildfire because it's different, right? It's different kind of sources, and flooding is different sources, but the temperature and the precipitation are this like 3 kilometers, and it's been, okay. So it's a totally different, when they do those local models that nest within the global ones, it's different. They're not using probably machine learning techniques. Tia, is that, I'm like tracking Tia in the chat. Yeah, I wonder how the methodology compares. Tia wants to know too. Let's invite her to coffee as well, Anna. You, Anna, Tia, and I, we'll have coffee and we'll talk about this.
Sounds like a good idea.
Yeah, and Alexis can come too. I'll send it around. We'll do another group meet.
Yeah.
Okay.
Yeah, let's get to Alexia Hoffman's question. Hey everyone, I'm Alexis Hoffman. Hello, Alexis. She says, I'm a climate scientist turned data scientist. I'm located in Boulder. Awesome. Well, I couldn't miss those talks. Excited to be joining you. Yeah, we are very happy to have you here as well. Looks like you guys are training with a GFDL model. How do you think these models would perform using another model like CESM or MIROC as inputs, particularly one with different regional biases? Do you want to address this question, Anna?
Yeah, sure. Hi, Alexis. I'm probably not the best person on my team to be answering this, because I'm like the one person who didn't come from a background in atmospheric science. But I can't say we have done this like we have used different data sets. So for the results here I was using a GFDL shield model, but we have also sort of used like a reanalysis data set as the target as well. And yeah, you're right. It definitely does change the resulting model. Like if you have a different bias in the training data set, you definitely see that in the online run.
Hmm.
And if you like have one that's too biased, then it tends to just lead to more instability and crashes and drifts.
And that initial graph that you showed, where it showed the kind of incredible disparity in different people's forecasts for precipitation, is that different regional biases? Like, and they're all kind of capturing the global picture still, or what was that like? I know or is it, just like not elements of that in it? It really just is like you parameterize these things differently and they will come out with, outrageously different numbers, even if you're using kind of the same inputs.
Sorry, so you're asking like if you start with the same inputs and just have a different parameterization, like is that
Well,
what's
no, I mean,
leading
I
to
know
the
if you have a
sky?
different parameterization, it'll make a big deal difference. But like when you showed that graph, right, and you showed all the different forecasts into the future, my first thought in my mind was, are they, I guess, like this idea of like the regional, like if I'm trying to target, or if I have better data in some regions versus another, or I'm, in terms of what you're capturing, like where, I don't know, but maybe it doesn't even work that way. Yeah, like a regional bias that kind of goes through. But
Like, are there some regions that have more agreement in models than others?
Maybe.
Yeah, I think there's definitely like some there's like global maps that can show you like the spread in the ensemble for different predictions. Yeah, I'm not too familiar with it though, but I bet like the climate science the people with like climate science backgrounds are all like, those regions.
We should definitely start a climate scientist group within our online machine learning data science group. And we also are planning to have a second round of talk about climate change. So hopefully more people will be connected at that time. Yeah. Nice. Okay, we got some more questions coming. So actually, I posted a question like I'm not quite familiar with climate scientists, but climate change models. But I'm just curious. I see you are dealing with a lot of data. I'm curious what tools you use to do the modeling. Like, do you use Spark? Do you use Python? Or do you use R? Or is it any specific languages or tools that's particular fit for climate change models?
Yeah, that's a really good question. So actually a lot of the work that our team does when we're not like, actually the minority of our time is probably like tinkering with like the ML side, and it's actually a lot of infrastructure work. So we run all of this on the cloud.
That's everybody.
Yeah, so we have a really nice workflow, and we've actually written a Python. So this is all in Python. But this GFD model is originally it's Fortran code. So we have a Python wrapper for the Fortran that actually calls a Fortran and runs the model, and that makes it a lot easier for everyone on the team to sort of develop and try out new stuff because we're all a lot more literate in Python than Fortran. Yeah. And it's also nice because like we also like use like containers and Docker and stuff, and so that we can replicate this and we can run the same code on our laptops, or we can use Kubernetes and just have a container running in the cloud that has the same model and reproduce our experiments really easily.
Yeah, that's awesome to hear about. Yeah, like I feel like I'm also very interested in climate change model. It sounds like I can also start some fun project using Python. Like when I see like all the model like numbers you guys posted, I got like a little bit scared. Like I've never seen those models before, but it's good to know like a lot of tools we are using are like in common. Yeah.
Yeah.
A lot of audiences are like interested in trying out some models as well. Yeah.
Yeah, and my teammate is, if I can forward this to the group as well, he's going to release, I think some instructions where it's literally like a few lines. You download our public code and just run this model on your laptop if your laptop can handle it.
Cool.
Oh yeah, that's super cool. Yeah.
Yeah.
Do you have like a group of ML engineers and build a pipeline for you guys? Like how does it work? Or do you actually pick up a lot of ML engineers yourself?
We are all our own ML engineers. Yeah, the people on my team are like really, they're really great, both scientists and engineers. So it works out pretty well, actually. We don't really have specialized roles for the engineering as much.
Got it. Cool. Very cool. Yeah, and I see Amanda posted something so interesting to see the differences produced from the high res target and ML model. Super interesting. Thank you, Anna. Yeah, it's awesome talk. Yeah, I see. We still have 3 minutes left. I wonder if people still have any other questions. Are they still taking the time to type in questions?
Yeah, what's next? Okay. You know what I mean? So what's next on your pipeline?
Yeah, so what's next? We're trying to get a couple papers out.
Oh, cool.
Yeah, so if you're, look out for those. Yeah. And then we're doing a lot of, we're actually trying to get a lot of, this is around the time where we're actually like making a lot of stuff more public. So like if you're in the, if you're in the modeling community, we'll have a lot of stuff at the AGU meeting, the virtual AGU meeting this December, where we're just going to try, get this, show people like how nice and easy it is to run climate models in the cloud with Python. Yeah.
That's cool. Yeah.
Yeah, I'm actually really excited about our Python wrapper for the GFDL's FE3 model. I think it makes like running these simulations so easy for grad students and other people.
And what is the so then you guys do this work and then you show how easy it is to run these models. But if you ran the models and you created the predictions that are localized, what would I want to do in addition? Like, what would I want to change that would either customize it for my use case, or are you guys also just producing like a highly granular raster file of different time shots all the way into the future that you're also going to like make available for people to use? Or you know what I mean?
Yeah, like what's the final product?
Yeah. What is the final product?
Yeah, so the final product probably isn't going to be a data set. It would probably just be more the code and the model.
Okay.
So like it would be cool if like we could, if we could show that these machine learning parameterizations improve the skill sufficiently that that GFDL would want to incorporate it into their next iteration of their climate model or something like that.
Oh,
or
okay,
like,
cool.
Yeah, or if like, oh, these improvements to the weather forecast are good enough that that like NCEP would want them in their meteorological model or something.
Yeah, cool. Okay, cool.
Yeah, awesome. Yeah, thanks for the discussion. Like, really always glad to see our speakers and audiences are so engaged. Yeah, thank you so much for giving the talk, and it was really amazing. And thanks for the audiences for so involved for those questions. So let's move on to the second talk. Right. Let me just introduce Skylar first. Okay, let's share my Chrome. Okay, I guess so. Oh, it's working. Okay. Yeah, so our second talk will be from Skylar. Dr. Skylar Olsen is a principal economist at Climate Check, a new startup dedicated to providing easy to understand and detailed information about the climate change induced risks to properties, lifestyles, markets, and communities. Dr. Olsen is passionate about unlocking academia and the proprietary data at big companies to bring understanding to everyday people who can really use it. An acclaimed public speaker and established commentator, Dr. Olsen has regularly appeared on stage in print and on local and national broadcasts and radio stations across the country. In April 2019, Dr. Olsen has the honor of testifying before Congress Housing Financial Services Committee on fair housing issues. Previously senior principal economist and director of economic research at Zillow, Dr. Olsen was a foundational member of the public-facing economic research program at Zillow Group and directed many of Zillow's data sharing initiatives over her 8 years of service. She holds a PhD in economics and a specialization in econometrics and environmental and resources economics from the University of Washington, where she received an award for teaching excellence. Yeah, awesome. Yeah, thank you for serving in the fair housing issue. It's really important in Seattle area. Yeah, so without further ado, I will let you go to your talk.
Awesome. All right. Well, thank you so much for having me, everyone. Yeah, I see a lot of, Zillow kind of names or Emily's here. I see that, and other people that I've met, back in the before times. So what I'm going to talk about today, and for anyone who has known me, at the Zillow years, that like 8 years there, I've always sat kind of at the intersection of an analytics team and when it crosses over into the public sphere, right? So I'm kind of engaged kind of more than I maybe was at Zillow in determining what our product looks like or, how to do that. But I've always done kind of the research work kind of downstream of the machine learning analytics, more in the data science kind of skill set. And then the audience is not necessarily business leaders within the company, right? The audience is real people outside. And at Zillow, the audience was, media, and through them, home buyers, sellers, people getting mortgages, anyone who's participating in the housing market, and then housing professionals. And at Climate Check, the audience is the same, right? It's this idea of like, what information do you need to put in front of a home buyer, seller, homeowner, and then beyond that, just regular everyday people to kind of also have a better understanding about climate change, but it is done through a lens of housing. And so if you're deciding where to rent, renting is, over the next year, it's generally, not as critical that you understand climate change about where you're going to live over the next year, as it could be critical to understand climate change about where you're going to buy a home. It's a huge share of American wealth. And a big part of the way how we build wealth in order to pass it down to our families and build social mobility. And so it's an important thing to think about and talk about and inform these decisions. It's an also important thing for housing professionals to consider, right? So builders and things like that. So I'll kind of dive in, share my screen here, and I'll get some slides. So it's a similar problem where you're taking data and then you're trying to think about like, how do I present this information or how do I kind of take the raw stuff? And Anna, I mean, by raw, I mean, after wonderful people like you have been through it and downscaled it to a fine resolution. And now I have more, not totally atomistic, right? Because the resolution is still say, 3 kilometers on a side. In flood data, it gets much more narrow. Flood data can get kind of wonderful because you have the elevation from satellite imagery, so it can get within 10 meters, that's very exciting. But it's still, as atomistic as we can get with public sources. And then how do I translate that to homes? And then how do I then walk it to what an everyday person should or could understand about climate change? And this will be a journey, by the way. Climate Check is a startup, right? Like we're small and kind of really just building the business model and building the product. And but it is live and launched. So if you want to check it out, you can do climatecheck.com and you can type in an address and it'll give you some ratings. And so I'll talk a little bit about, what we're doing and kind of the data behind it. And I'll try and keep it pretty nerdy. Okay, but the shtick, right? Change is happening and it's going to be like really devastating, and I think housing is a wonderful lens to look at it because it's one of the few ways that people are forced to kind of think about an investment far into the future that's kind of related to their environment and their space that they, are in, right? So it can be, and it becomes very emotional and provocative. It's hard, to tell someone, hey, care about climate change. And the examples I'm using to a mother of 4, is like, oh, it's the polar bears, it's the ice caps, it's this other place over here. If they're in their own world. And so the idea is, how do I get it, down to them? And then the other thing is to really think about it and kind of motivates what we're doing here and why, right? Is one, it's comforting to think that 72% of people think that global warming is happening. And if you look at this map, it's all orange, and orange is over, a majority of people are like, no, this is real, this is happening. But we still have this understanding that there's a very vocal and loud minority that doesn't believe climate change is happening at all. That's 12% across the nation. I think that's actually very high, even though, you can just frame it the other way and say 72, it's such a big number. Yay, everyone really agrees. But the fact that we have 12% of people who think that it's not even happening, we haven't even gotten to a question about whether or not it'll impact you or whether or not it matters where you live, and what you'll do about it. Will you vote? Will you whatever, right? We're just like, it doesn't even happen at all. And so this idea of putting it into the terms that you can understand, what will climate change mean to you locally, is one of the best ways that I think we can talk about climate change and actually move the needle on action. And I don't just mean, personal action, like we all come vegans. We also just need collective action. That's become, highly clear. And I don't even just mean like collective, I come from a space where, startups and Zillows, right, where you build a business model that radically can change the way a market works, or you can radically change the world. I love that idea too. Policy is going to be a big part of it. But what can you change about the way that the industry thinks about risk, so that property insurers change the way that they set premiums on risky areas, and then that impacts home values and less people will run in to move there, those sorts of things. And actually that's a big mechanism, right, that we imagine will actually kind of really start to evolve where people are when it comes to climate change, and try and gradually move people away from riskier regions, is through things like property insurance, property values, what you expect your equity to do, and whether or not you get a mortgage, right? Because mortgage companies and insurance companies, they're kind of collateralized against this portfolio of homes, or from the insurance side, your incoming premiums, have this pool of money, and they might go out, and I might have to dump a shit ton of money out into the world, if I have too much property risk. And people are talking about this as systemic risk. Markets won't be able to respond though if they don't have that risk information. Only the big guys really have access to expensive consultants in order to figure this out for them, for their portfolio of homes. So what's the answer for the little guy? That's the climate check kind of idea. So trying to get into a space where, you are providing easy to understand information is maybe not even is like almost too specific, because you also run this tension of, you're talking to non-analytics types. There's a comfort there to having a number that's relative, right? I have a score of 1 to 100, right? That gives me a relative risk on the risk that I'm talking about. So, for an everyday non-analytics type of person, there's a value to having that kind of image. I think it kind of makes it a bit easier. You can kind of see a signal, have an evocative response to what that is, and then move on with your decision making. Or you can get more information about what that experience might be. And so we try and surface the data in that way, as friendly as possible. And so this is our first iteration. So the example for temperature, would be, this example, you have a temperature risk of 49 out of 100. And I'll describe what that number means, but it just gives you this relative range across the whole US, right? Compared to other places in the US, you're pretty average, right? In terms of your temperature risk. Now, everywhere is gonna get hotter. Most of the time when we talk about temperature, it feels like we talk about, the average temperature, and it seems like such a small change. That doesn't really, move people and get them, I don't want to say I'm trying to be a Pollyanna in front of, real people about climate change, but I want them to feel urgent, right? I want it to feel urgent. And so the other thing that climate change will bring is more extreme events. So we're going to couch it in terms of how your experience with temperature will change in a way that you'll really notice, right? So this isn't a great example because it's, moderate risk or things like that, though everyone's temperatures will increase and you'll have more extreme heat days. But a great example to use would be like Maricopa County, which is what Phoenix is in. You would already expect to have, so in the model for 2020, you're already expecting to have 20 days over 110 degrees. I already can't fathom that as a Pacific Northwest person, what that is, 20 days over 110 degrees. Into the future, that'll increase to, twice as many, right? And that's a lot of time to be spending above 110 degrees. So that'll put, well, once you get to those kind of extreme temperatures, that's heat stroke for the elderly and those that work outside kind of conditions. So there is, a mortality element to temperature. But some of the risks here that I'm gonna briefly mention are things about catastrophic property damage. For things like temperature, this is also about adding resiliency, right? People already are moving to Phoenix, even though it's 20 days above 110 degrees. Some people like it. It's one of the fastest growing metropolitan areas. It has a lot to do with its affordability and its job growth. So you got to balance, those two things with kind of what we got to do for climate. But it does mean that you're running your air conditioning all the time. It's going to get worse. And so those air conditioning costs are going to increase. What do you do to your property, right? Is it new windows? Is it, there's lots of new technology about new paint that can reflect the light better. So it actually, makes your home cooler. Or down to, adding more greenery can lower the temperature as well. That'll be, your water bill will be intense in Phoenix if that's the option you use. So it's also about kind of helping people get ready. It's not just about don't move here because, catastrophic risk, but, how do we just talk about what climate change will feel like in order to get people more willing to take action and do collective changes. So really quick, just talking about our methodology and what we're doing, kind of more across the board here is that we're trying to present these climate change related hazards. So wildfire, heat, storm in this context does not mean storm surge from hurricanes in the way that we're actually modeling it here. And I think we stopped calling it storm. We started calling it heavy precipitation as heavy precipitation risk. So the idea that if you have a lot of snow at one time, that's roof damage, right? If you have a lot of rain at one time, that's erosion, mudslides, that kind of thing. Flooding is separate, right? So flooding has not just, I think the climate change version of flooding is very provocative. It in terms of coastal sea level rise, right? Places that are going to be permanently underwater. But many beyond that, it's high tides, it's storm surges, right? So sea level is also higher, and now I have more violent storms, so that'll go even further inland. Storms will be more severe. And then inland floods will also be more common because, as everything dries out and the air becomes less humid, it doesn't do a good job at regulating itself, and you get more volatility in precipitation as well. So it's weird, right? It's hard to talk about to lots of normal people. You're going to be more likely to have droughts, but you're also going to be more likely to have storms. So then what does that mean? But trying to present people that information. And Anna, here's I know you can't really tell the resolution, but you can kind of see, drought has much less fine resolution because these are watersheds, whereas storms, which is precipitation, this is the similar model data set, storms and extreme heat. It's both comes from a similar, modeling of meteorological. Fire is the MC2. Fire is complex, man, because it's temperature, precipitation, soil moisture, and then also the vegetative cycle, right? How do you kind of forecast that out? That's a tough one. This is probably the most stochastic of our risks, is fire, and yet it's the kind of one of the most provocative. So it's certainly something to talk about. Here's kind of some of the ways that you can kind of visualize or thinking about the flood that we go through, but let me quickly go to my command center. Okay, so we're in the business of taking data to real people. Now there's the atomistic data. You can type in your address and you see these scores, and you as the consumer now experience this interface, and you get a feeling about a different area. You can compare different properties. Maybe you're not just an everyday consumer, maybe you have a portfolio of homes, you're a mom and pop landlord, that kind of thing. You can experience it that way. But a big push of what we're doing and what I do in particular is I'm going to now talk about trends, right? I'm going to talk about what's happening where and kind of take it back up to a market. I'm an economist, by the way, by trade. I know we did that bio in the beginning. So as an economist by trade, it's, to me, you know, in order to talk about things, it's hard to say like, you know, that house on Main Street, they have that risk like this, right? Instead, you got to say San Francisco versus Sacramento, right? You know, more inland, or you talk about, you know, an interior county, you know, King County versus moving out to Snohomish, right? You have to make these more colloquial comparisons to people. So let's go to my command center. I'm going to do the big gnarly command center first. I call my Tableau work my command center because I put a bunch of stuff in it, and then I have it open whenever I talk to media, and I can kind of pull up different ideas in order to talk about them, in order to kind of cast it. So here is, I just talked about Maricopa County, right? So currently 21, sorry, I got it off. It wasn't 20, it was 21 extreme heat days expected, currently over 110 degrees. But later it'll be 46, right? So that idea of like just so many more heat days. And if you look at the heat risk, and here again, okay, and I should define, this is interesting. This is some of the nuance with how you kind of have this conversation and how you present this data.
Are you showing the Tableau?
Oh shoot, is it not? Yes, I was.
Yeah, it's not.
Okay, stop share screen, Tableau. Okay, so you can see here this, this was the Maricopa County. I hovered over to give those examples. Notice that I'm in a situation where Maricopa County is so very hot. It's going to get so very hot. I mean, golly, 46 days over 110, but it only has a relative heat score of 71. And a lot of that has to do with the fact that, you know, for people in Phoenix, that's something that they're used to. The infrastructure can support that much air conditioning. It's already had a lot of air conditioning, can support it, right? There are places where they're going to get much hotter, but they start from a lower temperature. So that change in heat is much more significant for them. And that makes them have more extreme heat days. Because one of the ways that we define an extreme heat day is to look at your historic average. So previously, what was a normal temperature for you? And then what do you expect in the future? It's going to stress your infrastructure if that heat increases a lot. You're going to run air conditioning more if you even have it. I don't have air conditioning in the Pacific Northwest, right? So if I get a day at 90 degrees, especially if I get a few days at 90 degrees, I'm feeling it in a way that, you know, another 100-degree days in Phoenix, you know, might not really matter. And so, you know, one, trying to put the data in a way that you can understand locally, in a way that will actually impact your life, right? Your lifestyle. That's one of the challenges of like how you model that together. They should actually mention, in order to take those granular, so I have this raster file, right, down to a certain granularity that's been downscaled, kind of some of the techniques that I like, one of the outputs that Anna's team, you know, people that use Anna's modeling would use, and then they create these more higher resolution. We would ingest that. I have that now at a raster in order to create these county level numbers, and I have city level numbers and lots of ways to talk to different people about the ways that the country is different. But what I'm doing is I'm just taking the population within each one of those same grids, you know, a similar raster file, but for population. And then I'm using a population weighted average of those risk scores. So then I can say something like the typical risk in Maricopa County is, and then have that conversation with people. Wildfire gets weird because they always want to know like the total acreage burned in a place, you know, but a lot of the burning gets done far away from residential areas. And so that's actually, it's just a funny way that you talk to the media about things they want to know about, this millions of acres that will burn. And you're like, well, I mean, that matters a lot, right? But if you're kind of thinking from your personal perspective of what, you know, you're going to do, it's more about the likelihood that, you know, it'll burn near you. And so then how do you present those risks? And then talk to the media in a way that seems fair or still the way they want to talk about it. Anyway, I want to give you kind of a little bit more insight into this, you know, like how do we put these things together? I'm giving you the full distribution across these counties, and they've been population weighted. So this actually approximates the distribution of those cells. because the cells are, whatever it does. And so here we've got these distributions. These are like the cumulative distribution functions. You know what I mean? Like it's the shape of it, right? So seeing like how many properties are above this level, this is what the shape kind of evokes here to look at it all. So you can see what underlies this risk rating. Remember this friendly score, that's someone can kind of see, they can know that what underlies it is extreme heat if they hover over, right? But think of it as kind of like this credit score to give people to kind of have a quick and easy understanding of it. If are people math averse? Is that what I'm saying? If they're analytics skittish, I guess, I don't know, but and then having these colloquial definitions, you can kind of see how they match up, and they don't match up perfectly when I rank by the rating, is because we also want to weight on the change in the increase in extreme heat days, right? This idea that I'm going to penalize you if your heat gets worse, right? Because it's going to stress your infrastructure. So it's not just having extreme days, it's having more extreme days that is going to be what affects people's lifestyles to move forward. Let's see. When did I start, Sophie? What's the timing I have?
Yeah, it's like your session is to 6:10, but we can go a bit longer if you want. Since
okay, sure. I just, when I have this much data, I can talk for a long time. But I do want to just show maybe on this one before I get to wild. Well, let me talk about the storm risk. I want the full distribution, not just trying to find outliers for people, because media likes outliers. So sometimes it's funny, like when we're modeling, we don't like them, but then they can be pretty provocative and kind of give someone an example. So you can kind of pull them up. But let me actually that was a storm risk rating. So I just want to put a caveat. I know that these are not public facing visuals, you can't see all the numbers, like I might hesitate to bring this into to some leaders because I'm talking about a full distribution. I might instead, show them something a little bit friendlier, like this. But I kind of thought you guys would like the full distribution to kind of think about, because it helps also tell you what the rating is. So storms, when you think about what's going to be rough about more volatile precipitation and how it will impact at the house, like the household level and how you experience it. It is, yes, the same thing. It's an increase in extreme precipitation events. So this storm is, there are two elements here. It's this extreme precipitation event. And you can see that over time, we're going to have more extreme precipitation events, right? So it's going to get more volatile. That's something that climate change will bring. The way that we define an extreme event here is you get more water over a 2-day period than you would typically do in, I think it's the 9, I want to remember the percentile. What's 8 divided by 365? It's like the more, it's on 8, like more than 8, the worst 8 days of water kind of is one of the ways to think about it on average each year. Yeah, so the worst 8 days of water. So that's how and that's, historically, what are your worst 8 days a year historically in your area, localized, right? And that defines an extreme event. And then how many of those extreme events would you experience into the future, and how much would that change over time? Because it was an extreme event if it was only 8 days then too, but now, you're going to have more than 8 days. You're going to have many more than 8 days in some occasions, a lot of water. And this, it's not just how many events though, because I'm going to have more often, I'll have extreme events, but those events will be more extreme. So it's also the amount of water that falls over that period of time is also increasing. And when you think about storm risk, you are thinking about the Olympics and a little bit of the Western Washington, where a lot of the Zillowites in this room, kind of live. And so, we live in areas that have a lot of clay pipes under the ground. We have lots of hills which are kind of tricky for erosion. More rain will definitely, challenge that kind of that environment, to say nothing of areas. I don't know if infrastructure wise we're in trouble here, but there are a lot of places in the US that are in trouble because they don't have the sewer systems that will be able to handle that kind of a load. So you'll have more inland flooding just from this kind of heavy water. And that's actually a big deal if I go back to the map, more for the Northeast. So if you think about where extreme precipitation risk is. So it's pretty much us in the Pacific Northwest, it's what we're very known for. And then it's really kind of out east, right, is where a lot of the water, this will just be an issue. And again, it's kind of your mudslides and your erosion and things like that. Okay, so I'm gonna, before I'm done, show you, not really my command center, but now this challenge. So this challenge, if you think of, can you still see it? Just, I switched tableaus. I don't know if you can see the new tableau. I'll just switch tableaus.
Oh yeah.
So if you think about the current challenge when we talk about wildfire risk, it's that everyone sees the outlier events, these extreme events in the news in California. And now if you want to think about how people handle risk information, the human brain is very weird. We love the extreme events, right? Like I remember reading a paper once as an economist, well, I am an economist, I just mean like in grad school, and it was about mad cow disease and how irrational people were about mad cow disease. It's such a rare, it is so rare, but it's provocatively awful. It's awful disease. And so many people, if you have like one event, an incredibly low probability of risk, but you have this one event, right, that's pretty sensational, and suddenly so many people stop eating beef, right? The behavior is kind of extreme. Wildfire is kind of a similar problem, right? It is absolutely an issue. It is absolutely going to become more common. It already is fairly common though, which is one of the problems with this, is like so one of the problems is that the way that the modeling works, right, is that the conditions will get worse over time for wildfire because we're more likely to have droughts, right? And if you think about an extended drought, that dries out the large vegetation, and then you have intense periods of water, but it's not regular enough to have a thriving soil base, and things like that, so that it can be held in by vegetation. It's like maybe a winter dump of water. Winter dumps of water, though, are great for grass, right? Grasses grow very quickly in that kind of environment, especially if there wasn't larger, healthier vegetation, in place, or that kind of middle tier. And now you've got perfect kindling once you have another extreme summer, right? So we actually, this past 10 years, beyond the kind of normal climate change arc, these past 10 years have been perfect to develop wildfire conditions, absolutely perfect. That's why the last few years have been so incredibly extreme. And climate change has been a part of that process. But when we think about into the future, where are the places that are risky, where are they not? Part of what the MC2 model tries to do, because it's a fair thing to do, is to do the feedback loop. If I have an area that is burned significantly and a lot of that vegetation is gone, then I will have a period of time where I'll have lower risk, and then that vegetation may or may not return. If the environment gets so dry, so hot, vegetation may not return. And in some areas, wildfire risk may actually go down, especially if you peg it through time. At what time? When do you expect the next fire to happen? But the problem still remains that the way that people are making the decision is off of the extreme events, right? So I might think to myself about, oh, California is the place to avoid. But really, the places where wildfires are very likely is not just California. Actually, Salt Lake City rises to the top in terms of the probability of having a wildfire surrounding you. I should mention real quick too that we are right now incorporating into this model. This right now is absolutely reflecting the probability of an event, like a wildfire event, or kind of how much area is burned, as opposed to the size of the burn, right? Like how high are the flames? because that actually matters a lot for property damage. So that's something that we're incorporating in, right now to be available in like when we'll be done with that? Gosh, hopefully soon, but that will change these kinds of numbers, and it might actually, take Salt Lake City down lower on this list because they're kind of like Southern California and they're dry grass and they're chaparral. It's a high likelihood of a burn, but will it be as horrible and horrific as if you have an unlikely burn in, say, the Pacific Northwest, where it's much less likely because we have storm, a lot more precipitation is expected. We're not expected to dry out as much, less drought risk, where we are. But if you have a burn and the trees and the vegetation is that big and it gets going, that's some pretty serious property damage potential, pretty serious stuff. And so that's something to incorporate into this one. But this is this probability that a burn happens near you, that you'll have to deal with smoke, surrounding your home on a given year. And Salt Lake City is actually going, into the future, 2050, these forecasted models out, will be worse, than your Californias of the year. And yet we're thinking so much, I think, about California when we think wildfire risk, but Eastern Washington is also very high on this list. And so is Southern Oregon. Again, not the Western because it's still pretty wet, but this is kind of more Central Oregon. But yet California is what we always think about, and so trying to talk about what that means. And then last thing, and then I'll open up to questions, is to talk about what does it mean, right? And are we making the right decisions? That's also the next step at Climate Tech, is kind of walking it from not just the probability that the hazard happens, but walk it towards the probability that you get property damage, how much property damage, or if it's more about lifestyle, right? If it's less property damage, but more, no one will want, less likely to want to live in a place where 46 days of the year over 110 degrees, then that's more about maybe just property value changes as opposed to catastrophic risks and property destruction. So walking it to your pocketbook, right? An individual's, how will it impact you personally, right? These hazards around your house is kind of the next step in the modeling, but this is maybe the first step of motivating doing that, which is to talk about the fact that there exists places that are at high risk for wildfire where we are building a lot. And notice I said there exist places where this is the case, because it's not true that it's systematically related. It's not true that we more often move to places that are riskier. Though there is like some of that, we more often move to risky places, but we don't more often move to the riskiest places. The reason why we move to the more risky places over time is also because we are, affordability pushes people further and further out. So you're into the urban wildland interface, right? And so you're more likely to be building in areas that are a little bit risky, but you don't necessarily more often build in the riskiest places. But there exist examples of very high risk and significant building and population growth in recent years. Yeah, so I'll end there in terms of kind of like the data to talk about, and then open anything up to questions.
Yeah, awesome. Yes. Yeah, I really like you showed a lot of changes, not only about the temperature getting hotter, it's also about like just the weather just become extreme, like small storms, small droughts. And I think that's something like it's kind of new to a lot of people. Like a few years ago when climate change has a name of global warming, like when I feel like when I talk with people about this and people like, I don't feel it's getting hotter, and this is like, but also like,
or
like
they might even think to themselves like, oh, good, I don't like the cold.
Exactly.
1 degree hotter would be good for me. And you're like, okay, hold up.
And I totally agree. I feel like those extreme events, they are kind of like the trigger of people alert, like climate change is happening. Like they not only just affect the temperature, it also affects the nature, the plants' life, the animals' life, humans' life. Like people lost their lives in the wildfires this year in California. It was really sad. This is a really important topic.
Yeah. And actually, I kind of want to mention too, I focused on temperature, even though, it's hard to say it's like, oh, property risk within this housing space, but extreme heat is the biggest killer. I don't mean to be like crazy, weirdly sensational. It's just true, right? It's like wildfire is violent, floods is violent, extreme heat leads to the most life lost. And it's not your whole, it's generally more, the way that we model it in kind of this space, in kind of the public health literature and things like that, is years of life lost, right? Amounts to how many total lives, but it's your mortality as an elderly person in an extreme heat event, can be pretty serious. And then those that are seasonal workers or construction who have to work outside, right? That it happens. So
that's very good point. Like, historically, when there's a cold, we just put up a fire, from thousands of years ago, we know how to use fire. But when it's hot, we can't go anywhere except using air conditioner. And for people like us, we live in the Pacific Northwest, we don't have air conditioner. And there are a lot of people in the world, they cannot afford air conditioner. Like, what are we going to do? Like,
well, and if you think about California's, energy grid has to turn off during the summer because too many people are using air conditioning. So when there's extreme heat, then they have to, ration it to energy for people. And that's not a third world situation. That's like lots of people in California all the time. So other places will start to experience that more and more. And I should actually say, like, right now at this point in Florida, Florida has to really support the home insurance market, in areas that will be flooded, right? Because it's hard to get a kind of an unsubsidized insurance policy in that space, right? If the home is going to be at likelihood to flood so often. California, had to pass a law this year that said, hey, homeowners insurance people, you cannot cancel someone's homeowners insurance until, for fire risk until January 2020, or excuse me, 2021. So, that'll come up, and then can, California homeowners in these areas get homeowners insurance? And that's an abrupt way to find out about climate risk, is like, suddenly I can't get my home insured, as opposed to, we should be having this conversation as normal people. And that's what I'm trying to do, right? The normal person conversation about climate change.
Yes, that's really important. Like, I see other folks posting questions. So Leslie says, are there risk rating available to individuals, for example, home buyers?
Yeah, so that's the product that Climate Check is building. So if you go to climatecheck.com and you type in your address, that's the user interface, the product side of it. You can kind of think of me as so Zillow actually used this model as well. This is like the Zillow playbook, early days. You don't do advertising, you just take this incredible asset that you have, which is data that people want to know about, and you do market level or community level research on that data in order to, get attention from media, right? So it's a public relations and media play as opposed to advertising. Instead of buying your attention, I am earning your attention with showing you my data. And in that way, I build trust and credibility. And so that's my role at Climate Check. Well, except it's a startup, so my role is like all sorts of things. But that was my role at Zillow and kind of the skill set that I'm bringing to Climate Check. And then hopefully also making Climate Check's products better and more actionable, right? So it's not just for those that need it, right? So maybe someone who's a bit more professional, instead of a score, of 1 to 100, you get, a likelihood of property damage, of totaling 5% of your home, in this case, that case, something a little bit more detailed to those that are more financially literate who want that information.
Yeah, definitely. It's going to be super useful. Like, I'm also trying to think about buying a home. Like, I go to the Bellevue right now, like the city map, it says have this flood, like earthquake and like droughts, wildfires.
Oh, yeah.
And with climate change, maybe the floods, the possibility of getting flooded in some certain neighborhood will increase. Definitely very, Yeah.
The Pacific Northwest is pretty lucky, except for the storm.
Yeah, let's see how long that can last.
Florida is very challenged. Louisiana is going to really struggle. I don't know that Arizona is going to struggle. Like people already love to live in that heat. I have family in there and they just tell us, they're like, oh yeah, it's we hit 118 today. And you're just like, why are you not like upset?
Yeah,
like living your life. Okay.
Yeah, let's see.
People have different preferences, I think, is another kind of lens. Like how we handle this problem. We need a lot of major change, but I don't think we can expect people to suddenly become different people. And they're very different people and they like to live in different areas of the country for different reasons. And so how can you work within that? I think is also another way to think about it.
Yeah, definitely. Yeah. So we see Amanda says a point that struck out for me was considering the extreme heat and not necessarily seeing normally hot places get hotter, but seeing the rising hot days during a Seattle summer and the infrastructure that isn't in place for this. Yeah, that's like very good. Yeah, point.
Yeah, here, and I'll even hover over the one for Seattle. So you can see those numbers. I don't know. You can also kind of look up your own property in Seattle, and I think you'll see similar numbers because ours is, population weighted. And if you're in, the more dense areas, it should kind of reflect that. But we can go back to the command center and I'll hover over King County. So in King County, we're so wimpy up in King County, right? An extreme heat day up here. It's just 81 degrees. We're lame. I feel it when it gets 85, like I feel like it's very hot. When I visit my mother-in-law in Orange County, I don't like it down there. It's too hot. It's, California is beautiful, but it's too warm. So currently we would expect 15 days over 81 degrees due to climate change and the rise in extreme heat. These models predict 20 days. So that's air conditioning territory,
Yeah.
All right.
Yeah,
Stop
we see
right
like yeah, we see like Tia also commented, I'm reading a book by one of my favorite authors, Barbara Kingsolver.
Oh yeah.
Fight Behavior, which is an interesting novel exploring a fictional example of climate change impact in Southern town and societal differences between the conservatives and liberals. I found thought-provoking. Oh, nice! I need to add that to my reading list.
Yeah. Oh man. Yeah. Actually, so can I lay on a little bit more kind of points?
Yeah.
Okay. So there's this great paper by Asaf Bernstein, and I kind of think about it and use it a lot in the context of why you have to provide information like this and how should we be providing it. So he did this research that looked at what is going to be the impact of sea level rise on home values, right? And do we already see that impact? And one of the things that he did was he, broke out, he looked at residential, commercial, and just rents, right? So commercial properties. And no matter where I was, liberal or where he, where he did the analysis, liberal or conservative areas, if it was commercial real estate, you saw an impact on property appreciation in areas that were going to suffer from sea level rise. And he was controlling for things like distance to, the water and elevation, except, so you're trying to get it so that the only variability, in your model, and we're economists, so it's not a machine learning model, right? It generally has, some explainability to its, coefficients that come out of it. It's kind of what we tend to do, what makes us different from the machine modelers. Though there is actually a blending of those now, and I'm very excited about the technology. Maybe we should get together and talk about that. But anyway, no matter where they are, the appreciation on commercial properties was lower if it was in an area that would suffer from future sea level rise, right? Because these are people who are thinking long-term investment perspectives, right? And they're looking at the data and they're figuring it out and they're saying, is my investment going to be safe? In residential areas, it was only in liberal counties that you saw an impact on residential property values. In more conservative places where maybe you don't believe in climate change or you are not surrounded by the information about climate change through the media that you watch or whatever else, you continue to buy just as readily in areas that will be underwater. And to me, that's thought-provoking.
Yeah. Yes, I definitely remember seeing some news like homeowners in Florida, someone like trying to selling their homes, like they don't like, you know, homes is kind of like something we can leave to our next generation children.
Yeah.
Like they don't want to become as a boat. That's not a great
yeah.
idea.
No. And there are already plenty of places that flood. Miami floods like every king tide. A lot of the streets, you know, are just, they can't. So one of the biggest initiatives recently was the city, you know, everyone passed a levy to pay to get, you know, totally new sewer pumps, you know, everything, because the city is flooding now all the time.
Wow. Yeah. Yeah, thank you so much for your talk. It's very inspiring, and I look forward to see the product and the growth
Okay,
of the
good.
company. Yeah.
Yeah, we'll keep working on it.
Yeah, so let me just share my screen. We got to the third talk. Yeah, so this is from Katinka. She's actually in Italy now, so because there's a big time zone difference, so she recorded her talk in advance, and we'll play this video later. So Katinka is a climate scientist at the Institute of Atmospherical Science and Climate in Turin, Italy. She uses networks of ground and satellite observations, global climate models, statistics, and data science to investigate the mechanisms of large-scale climate variability and change. You can follow her research and outreach activities on her website and on Twitter. So I will first post her information in our chat. Okay, where is the chat? Okay, in our chat. And then I would start to, and also I will post her link in our chat in case the Zoom version doesn't work. So I will just start to play her video. And I go to.
And today I'm going to talk about.
Oh, sorry.
In addition to this exercise, to be sure about a prediction, we sure need to provide also rigorous leveraging.
Let me just start from
today. I'm going to talk about leveraging data science to reduce uncertainty in predictions of future climate change.
How do I go to the view, the full screen view? Okay, this is what I want.
Italy, my name is Katinka, and today I'm going to talk about leveraging data science to reduce uncertainty in predictions of future climate change. I am a climate scientist at the Institute of Atmospheric Sciences and Climate in Turin, Italy, and I obtained a PhD in meteorology and physical oceanography in 2015 from the University of Miami. Today, I'm going to talk about what I'm currently working on, which is the Atlantic Meridional Overturning Circulation, or AMOC. The AMOC is a global-scale ocean circulation that redistributes heat, carbon, and fresh water. The AMOC transports warm water from the equator into the North Atlantic, where thanks to the high concentrations of salt and the cold temperature, it becomes really, really dense and sinks to the bottom of the ocean, where it goes back towards the equator into the southern hemisphere. The AMO slowly circulates around the world, and for the water to sink in the North Atlantic, it takes about 1,000 years to resurface in the Indian and Pacific Oceans.
Oh, wow.
Understanding how the AMO works is at the forefront of climate science research for a very simple reason. Currently, the AMOC in the present climate makes, thanks to its circulation, the entire northern hemisphere about 1 degree warmer than the southern hemisphere. But the AMOC may actually completely shut down like it did during the Earth's history when the entire globe entered into an ice age. And this is relevant still today because observations of the AMOC or observations of variables related to the AMOC show us that in the past 150 years, the AMOC has actually been slowing down. And the reason why it slowed down is because of the increasing emission of greenhouse gases from human activities. This increased emission of greenhouse gases makes the temperature of the Earth warm, which causes the sea ice to melt. And this reduces the salinity, basically the salt content in the North Atlantic, which is the propeller of the AMOC. projections of future climate change actually show a further decline of the AMOC, but a complete shutdown is deemed unlikely, at least for the next 200 years. To investigate the impacts of future climate change, we run idealized simulations with global climate models, which are, in a nutshell, integrations over time of the equations that describe the Earth system. In projections of future climate change, these integrations also have an additional term that represents the forcing from the emissions of greenhouse gas forcing. These models are not to be confused with what everyone else would think a model is, which is this. In this figure, I'm showing the AMOC anomaly in future climate change in a number of models, which are color-coded here. Each color in this figure corresponds to a different climate model. If you look closely at these projections, you see that there is a big range in the possible decline rates of the AMOC across the models. And this is due to differences in how models handle the representation of the ocean circulation. For example, the model down here in cyan predicts a reduction of about 75% of the AMOC strength, but the models here above in brown, it's only a 2% decline. So this is a big difference, but what does this mean in projections of future climate change? You would think because the AMOC has such big different decline rates, that should impact climate change, which in fact it does. But until recently, the exact impacts of the AMOC decline were not known because the models have only recently caught up on simulating and understanding these processes. In my work, I investigate whether these different decline rates affects, in fact, simulations of future climate change. Disclaimer, they do, and let's see how. In this figure, I'm showing the projected temperature change in models in which the AMOC decline is different. So for example, in the panel above, I'm showing the average of the models in which there is a large AMOC decline in projections of future climate change. And then the figure below is an average of the models that project at a very much smaller AMOC decline. And units here in these figures are degrees per degree of global warming. So it's scale, in other words, is relative to the is relative to a degree of global warming. It's pretty clear here that in the models with a large AMOC decline, there is a much smaller temperature increase in this region of the North Atlantic, which actually coincides with the region where the AMOC waters sink to the bottom of the ocean. And this doesn't happen in the models with a small AMOC decline. So this is actually a big deal that the models project such different patterns of temperature change, because wind anomalies are largely influenced by the heat released by the ocean. Therefore, these different patterns of temperature change, they cause different wind circulations, which affect projections of climate change impacts over Europe and North America, such as temperature extremes, heat waves, droughts, and rainfall. To go a little more into details, here in this other figure, I'm showing the projected precipitation change. Again, above are the models with a large AMOC decline in the future, and below is models, the average of models with a projected small AMOC decline. So when we examine precipitation change, we see drastically different anomalies in the models with large rather than a small AMOC decline. In the North Atlantic, almost the entire basin exhibits a decrease in precipitation, and there's actually an anomaly of opposite sign in the small AMOC decline. Another example is here, the precipitation associated with the Indian monsoon, which affects millions of people. And in the models with small AMOC decline is a lot bigger. There is a much larger precipitation increase than in the models with a large AMOC decline. So I don't want to go too much into the details, but the main reason why there are these discrepancies is because a large AMOC decline partly counteracts some of the effects of global warming. to be honest, I find this amazing that an ocean circulation can affect large-scale climatic events, even rainfall around the world. With so much at stake, it is really important that we work on narrowing down the uncertainty in the projections of future possible states of the AMOC. The good news is that this problem is solvable, it's just not that easy. The models predict many future outcomes because they rely on internal parameterizations of physical processes, and all models have inherent biases. And by biases, I mean that in climate models, there are some differences from the real world, also in the simulations of the present climate, but there is no one model that simulates the entire climate correctly. So how do we go about solving this specific problem? First, we need to select the models that do a better job compared to observations of the real world at representing the physical mechanisms that are responsible for the AMOC to decline. But second, we also need to come up with a rigorous physical explanation for why we expect the AMOC to change in a certain way rather than the other. In climate science, we say that we need to come up with multiple lines of evidence to have confidence in our predictions. How can we leverage machine learning? From our analysis of climate models, we know that there are multiple variables in the current climate, which I'm going to call features from now on, that can predict the amplitude of the AMOC decline. One example is the models in which the salinity in the North Atlantic is large in the current climate, in a simulation of the current climate, then those models generally predict a larger decline in the AMOC. And like salinity, there are several other features correlated with the response of the AMOC to climate change. But we need to be able to tell which ones are the strongest predictors across all of the models and all of the variables that we consider. So if we construct a table of train and test data, each row will correspond to a different climate model. The tricky part here is figuring out what we need to put into the feature cells. Column of the labels, this is pretty simple because this is just the simulated AMOC change in each climate model. So this is difficult because we are dealing here with variables that have complex multi-dimensional patterns. For example, here I'm plotting one of the possible predictors, which is called mixed layer depth. You can think of the mixed layer depth as essentially showing the regions where the water of the AMOC current sinks in the North Atlantic to then make its return towards the equator and the southern hemisphere. Here in these figures, I bring up an example of two climate models. The model on the left projects a large AMOC decline, and it shows basically that in the mean climate, there is a large area of water mixing in these regions on the North Atlantic where you see the orange areas. On the other hand, this other model on the right is a model in which the AMOC decline is pretty small. And what it shows compared to the model on the left is that there's not much going on. That's like the strength of the AMOC and the mixing of the water associated with the AMOC formation is pretty small. So the problem with this is that there's not just one absolute value, but there is a complex spatial pattern. And so you need to be able to retain the spatial information in order to make a prediction of how the AMOC will decline. So this is clearly a difficult problem because all models, as I said, are different. However, there tend to be recurring patterns across these models. Hence, we use a method that is called the empirical orthogonal functions, or EOFs. EOFs are essentially a principal component analysis in multiple dimensions. In our case, we use it to extract the patterns that explain most of the variance across the models. And once we have 1, 2, or 3 patterns for each feature, then we can compute spatial correlations of how these variables look in each model with the leading 2 or 3 EOFs across all models. So this is the information that we are going to put here in the table of the features. For example, for a selected feature, say salinity, model A has a spatial pattern of 0.50 with UF1 and a spatial pattern of 0.12 with a UF2. And we do this for all models and all features in order to be able to fill this table. And then we feed this information together with the labels and a training set to supervise regression algorithms. Out of the regression algorithms, we obtain weights for each feature. From these weights, we're able to determine which features are the most important in predicting the outcome of the AMOC. Once we have this information, we can select the few models that are best at simulating the most important features in the current climate and see what is their prediction of future climate change. Now, this approach works in our particular case because I had a priori knowledge that models that with a certain simulation of the mean climate tended to predict similar rates of AMOC decline in the future. For example, as I mentioned earlier, the models with higher salinity all predict a strong AMOC decline. What this additional machine learning and exercise adds is that now I know which is the strongest or which are the strongest features among all possible variables that I'm considering, and how the spatial pattern for each feature looks like. With this added information, I can make a better comparison between the observations and the model. And I can select the models that are better at simulating the mean climate, thereby reducing the possible outcomes of the AMOC decline. In addition to this exercise, to be sure about a prediction, we sure need to provide also rigorous physical explanations for why we expect a change in the AMOC to be small or large. And as here I also illustrated one method to leverage data science and machine learning algorithms to approach this problem, but I'm sure there are several others that could be used, including image recognition, for example. And well, with this, I'll conclude, and thank you very much for listening to me, and please don't hesitate to ask any questions and contact me if you're interested in learning further about climate science and possible applications of machine learning. Thank you.
Yeah, awesome. Yeah, Katinka, she does such a professional job of recording her model and recording her talk. And when I was listening, I was thinking, oh, Anna has a model predicting, the climate change in the air, and then Skylar's model is about the impact on human on the ground, and Katinka's model is about the underwater. I was like, we just covered the whole.
I was nearly done. I was
Yeah.
ready. Yeah.
It was so amazing. Yeah.
Uh,
Yeah. Since she's not here, we can definitely post questions on the meetup page, and she said she's definitely going to take a look and answer it, and or if we have any thoughts, we can also chat it here as well. Yeah. Other than that, we still have 15 minutes. Originally I scheduled if we are interested, we can do a breakout room and we can do some social. This is also the first time we host online event. So before we would just, grab some food and social in the same room. So I'm not sure, do people want to do it, or is it if you feel you want to do it, you can post it in the chat or stay on the call.
Will it be chaos if we have 22 people? Isn't that much, right? Can
Yeah,
we just have everyone just chatting in this room?
unmute everybody. Unmute.
Yeah.
Yeah.
That's also a good idea,
Come
actually.